Hello, welcome to Understanding Power Electronics. Boost converter is a useful converter, but nevertheless, it does have some issues which we should be aware of. These issues are either specific to the boost converter and its derivatives, or they apply to boost converter and a few other converters. As a designer, as a user, we should be aware of these limitations and we should know the ways to mitigate them. In this video, we will go through a list of problems associated with the boost converter briefly and go through the ways of mitigating them if it is possible to do so. That's our aim. Let's get started. First, to start off this video, I'll present the list of problems that we are going to discuss in this video. First is output overload short circuit protection problem. I'm going to list these problems. We will go through these problems in greater detail throughout this video. And second is the startup inrush current problem. This startup inrush current problem has been discussed in greater detail in a separate video 2B-5. In this video, we will just briefly summarize it so that our presentation and our understanding will be complete. The next issue that you can associate with a boost converter is output no load problem. That is, if you don't connect any output load, there can be a problem associated with the boost converter. We will see what it is here. And the next issue is the output ripple voltage problem. The boost converter shares this with a few other converters. The next one is the maximum duty cycle problem. Why we should have a limit on the maximum duty cycle. And the last problem is the dynamic response problem. This last problem is quite important and quite complex in nature. It deserves a separate video or two. But in this video, we will present a brief insight into this issue. Before we start, a word of caution. Don't get put off by the long list of problems associated with the boost converter. Boost converter is a popular converter and used in many applications. We will now go through these problems in greater detail. The first problem that we'll be seeing is overload short circuit current problem. This is a boost converter connected to a load. Let's say we increase the load. We increase the load means we are increasing the load current. If you think of the load as a resistive load, we are actually decreasing the value of the resistance. Notice that from the source, there is a direct path to the load via the inductor and the diode. So the current can go on increasing, even up to short circuit. You do not have a mechanism within the boost converter to switch off the current. The output current can increase indefinitely without limit. So as the load increases, the device stresses will increase and you know what will happen under stress. I don't have a solution for human stress and overload, but for the boost converter, we can try a few things. One is introducing a fuse or a circuit breaker. The fuse will blow or the circuit breaker will trip and protect the circuit. Of course, this is a nuisance. You have to replace the fuse or reset the circuit breaker. Also, a fuse or a circuit breaker may not be fast enough to protect power semiconductor devices. So what we can do is to introduce a series power semiconductor switch. We can do it on the input side. That will be one solution. Here we have shown a power MOSFET Si in series with the inductor. When overload or short circuit occurs, that will be sensed and the switch Si will be opened. You can notice the problem here. Switch Si is expected to interrupt the current in the inductor. That's a no-no. That will very likely damage the switch Si. So you can put a snubber across the switch Si. Because of the large value of the inductance L, snubber requirement may be large. So the solution to that may be to use a freewheel diode as shown here. So when the switch SI is switched off under overload or short circuit, the current in the inductor will freewheel via the diode. Through this freewheeling action, the current will die down to zero. Notice that this part of the circuit looks like a buck converter. There is the same switch diode inductor arrangement. We are not using this part as a buck converter. We are going to use the switch only for overcurrent short circuit protection. So this is the input side switch scheme or input switch scheme. So this is one possible scheme. We can also try and solve the problem by introducing a switch on the output side here. So this is the output side switch scheme. We introduce a switch S0 on the output loop here, and that disconnects the load under overload or short circuit. So the resistance RS is the shunt resistance. It's a very small value resistance, and the voltage developed in that resistance is used to sense the current. So when that current goes beyond the threshold, the switch S0 is opened. This is the output side switch scheme. In both the schemes, as soon as overload or short circuit is detected, switch S is switched off. We don't want to make the problem any worse. So we can compare the two schemes now. During normal operation, switch SI is left on all the time in the first scheme, and in the second scheme, during normal operation, switch S0 is left on. So there will be some conduction loss in both the schemes. In the first scheme, the current is a bit higher, that is the input DC current. In the second scheme, the current will be a bit lower, it is the output DC current. But in both the schemes, there will be conduction power loss under normal operating conditions. One problem you can notice here, in the input side switch scheme, even after SI is switched off, because of the energy in the inductor and the capacitor, high current may continue to flow into the load for a bit more time. And so the short circuit current may flow for a little bit more time. The output short circuit current is not cut off cleanly. Whereas in the output side switch scheme, it is a hard interrupt. When S0 is opened, the output current stops. So that's a good thing. But on the other hand, there is one problem with the output side switch scheme. When the output side switch is switched off, the inductor will still have some current. So that inductor current is going to flow into the capacitor now. It cannot flow into the load. So the inductor energy will be transferred to the capacitor. The capacitor voltage will build up. That high voltage may damage the capacitor. It may also damage the switch or the diode. The next problem that we are going to see also arises because of the lack of a series switch in the boost converter circuit topology. This is the startup inrush current problem. Again, you notice that between the DC source and the load, there is a direct path via the inductor and the diode. So when we connect a source and switch on the boost converter, there will be an inrush current into the boost converter. We know that when a big sale is announced, at the start of the day, you will have an inrush of people into a store. Likewise, when the boost converter is started, there will be an inrush of current into the boost converter due to the charging of the output capacitor. Taking some values for the components of the boost converter and the parameters of the boost converter, that is the duty cycle and the switching frequency, the steady state output voltage and the output current and input current are given here, but we are looking at the initial transient of the converter. We can run a simulation. When we do that, you can notice that there is a big inrush of current due to the L and C resonance circuit. The peak value of the inrush current is 90 amperes, which is much more than the 10 amperes steady state value of the input current. The simulations in this video are carried out using LT Spice. A link is provided below. This heavy inrush current can be a problem. One problem can be the damage to PCB traces, diode, etc. Another problem can be the nuisance tripping of any circuit breaker or blowing out of any fuse on the input side. A third problem can occur particularly when the input voltage is current limited. If the input voltage source has a current limit, then it will not allow such a large inrush current to flow. It will drop its voltage to limit the current. Under that circumstance, the input voltage will suffer a voltage drop at the start. If other equipment, other circuit boards are connected to the same source, then those equipments, those PC board will see a voltage dip. That can be a potential problem. These are some of the problems that can occur due to the startup inrush current. There is an earlier video, 2B-5, on inrush current in boost converter, which goes through the issues related to the inrush current in greater detail. You may wish to go through that video. So what can we do about it? One way is to insert a resistance in series on the input side. The problem is if you put a large resistance in order to reduce the current substantially, that can of course increase the loss considerably. Another way is to use a power transistor in series on the input side. So during the start, you slowly turn on the power MOSFET in order to limit the current. And once the converter has started, you switch on the MOSFET fully. This can work well. Of course, since you have a series switch all the time, there will be some additional power loss. A third option, often preferred, is to use an NTC thermistor in series. NTC thermistor meaning negative temperature coefficient thermistor. An NTC thermistor is inserted on the input side. This NTC thermistor has a characteristics resistance versus temperature as shown. At room temperature, the resistance will be high. So when the converter is started, this resistance provides damping in the LC circuit and reduces the current. As the current flows, the NTC thermistor will be heated up. Its resistance will dramatically fall. So under normal operation, the NTC thermistor will present a low resistor on this input side. This is often a solution implemented in phone chargers and such applications. So starting can be a problem. Overload short circuit can be a problem. How about open circuit? Supposing I don't connect a load. I give a boost converter to an engineer and ask them to test it. The engineer might think, first let me test it under no load and then I will load it. That's what you do with a motor. When you are testing the motor, you will test it under no load and then apply the load. So you might think, okay, let's do the same. So you take a converter, you remove the load, you want to test it. Let us say in the design of this converter, the converter has some closed loop operation. Maybe the output voltage is regulated. It has some control system to go along with it. Let us say that we have specified a minimum duty cycle. In many converters, we will specify a minimum duty cycle at some low value, maybe 0.2, maybe 0.1. So there are two things happening here. One, we have removed the load completely. Second, we have a minimum duty cycle in our system. Now let's see the waveforms under this operation. We have a D minimum, so we have a T on minimum. Because there is no load, the operation will be in discontinuous conduction mode. The current will start from 0. The switch is switched on, so the inductor voltage is V in. So the current goes up at a slope of V in by L to some peak value IP. And then we switch it off. The inductor current falls. Depending on the capacitor voltage, it will fall at some rate and reach 0. Next cycle, similar thing happens. The average of the inductor current is the input current. I will mark it as I in. The fall of the inductor current will depend on the actual output voltage at that instant. Let's not concern ourselves too much with that. So the input current continues to be drawn. You know where we are going. We are drawing input power, but there is no output power. This part of the inductor current is the switch current. This part of the inductor current will be the diode current. The diode current is not going to the load. So the complete diode current goes into the capacitor. This delta Q is a charge going into the capacitor in one cycle. Capacitor voltage goes up by a little amount. The next cycle, again, a small charge goes into the capacitor. Again, the voltage will increase. So every cycle, you keep pushing a small charge into the capacitor voltage will go on building up. At some point, the camel's back will be broken. So the charge delta Q gets dumped into the output capacitor in each cycle. So that will continuously build up the output voltage. Another way of looking at it is the average diode current is the ID average. Previously, this average current was flowing into the load, but now it is constrained to flow into the capacitor. When this diode average current equals the internal leakage current of the capacitor, that is when the balance will occur. That might be occurring at a high capacitor voltage. The capacitor voltage will be equal to the forward voltage stress of the switch. So the switch may get damaged, the diode may get damaged, the capacitor may get damaged. So what can you do? You make sure that the boost converter will not operate under no load condition ever. Or if it must operate under no load condition also, make sure that the duty cycle can go down to truly zero naturally. The switch should be completely switched off. If you must have a minimum duty cycle for whatever reason and the converter must be able to operate under no load situation, then you can add a bleeder resistance to the converter. Of course, that will have efficiency implications. The next problem that we are going to be looking at is the output ripple voltage problem. It is more difficult to meet the output ripple voltage requirement with a boost converter when compared to a buck converter. This problem occurs in a few other converters also, for example in buck boost converter. In a boost converter, the inductor current waveform under continuous conduction mode is as shown. I2 minus I1 is the peak-to-peak inductor ripple current. The average inductor current is In, the DC input current. Notice that the peak value I2 is In plus delta IL by 2. So the peak inductor current is In plus delta IL by 2. Now this part of the inductor current is the diode current. We can plot the diode current as shown. The average of the diode current is the output DC current I0. The remaining part is the ripple current that flows into the capacitor and is supposed to be absorbed by the capacitor. So the capacitor current will be as shown. Notice two things about the capacitor current. One is the peak-to-peak ripple current is large, In plus delta IL by 2, which can be a large value. Another is the capacitor current is not smooth like the inductor current. It has sudden changes due to the switching action of the switch. Because of this, it is difficult to obtain good, it is difficult, not impossible, but difficult to obtain good clean waveforms on the output side with a boost converter. The boost converter shares this property with a few other converters such as the buck boost converter, for example. Suppose you have an equivalent series resistance in the capacitor. Then due to the high ripple current, there will be an additional ripple voltage developed in the capacitor. So the ESR can create a problem. In addition, notice that the switch, the diode and the capacitor form a circuit loop. Any inductance in that loop will develop a spike of voltage whenever there is a sudden current change. So because of both of these, you will find on the output capacitor the ripple voltage will be higher than expected. We can compare this with a buck converter. In the case of the buck converter under CCM, the ripple in the inductor current flows through the capacitor. So the peak-to-peak ripple current in the capacitor is limited to I2 minus I1, and the waveform is smooth and not chopped. So because of that, it is easier to obtain the required ripple voltage with the buck converter. Of course, in the buck converter, the input switch current is chopped, and so the input filter capacitor CI may have higher ripple than the ideal case. But as far as the output ripple is concerned, using a buck converter, you can meet the ripple specification more easily. This shows a simulation. The inductor current, you can notice, is pretty smooth. There is no issue with the inductor current. For this simulation, I assumed some values of ESR and ESL in the capacitor, and I also included some parasitic inductance in this loop. So you can see that you have additional ringing that is occurring, which increases the peak-to-peak ripple voltage considerably. So careful attention has to be paid in a boost converter to meet the output ripple voltage specifications. So what can we do about this? One is to make sure that in this loop of switch, diode and capacitor, there is as little parasitic inductance as possible. That means we place these components physically close together and keep the connection lengths small. The capacitor has to be carefully chosen. A few capacitor types may be parallel together. You may use a high frequency capacitor such as a ceramic capacitor, multilayer ceramic capacitor for filtering the high frequency part of the ripple current. So particular attention has to be paid to the choice of the capacitor. One may also think of replacing the simple capacitor with a third order filter, a CLC filter, so that the filtering can be done more effectively. So our expectations are for just a little ripple, we may be having big waves coming at us. The next problem that we are going to see is the maximum duty cycle problem. This shows the converter gain V0 by Vin versus duty cycle under ideal conditions. V0 by Vin value starts from 1 and goes towards very high values as D goes towards 1. This is the ideal case. In a practical circuit, due to losses in the circuit, the voltage gain curve is going to look more like this. It will start from close to 1 and then build up to a maximum value V0 by Vin max. That maximum occurs at some duty cycle, let's call it D max. Beyond D max, the voltage gain will start to fall. As you increase the duty cycle, the voltage falls because of excessive loss in the circuit. This is how a practical boost converter is going to behave. So let us see what the problem is due to this. Let's say we take a practical boost converter and incorporate it in a closed loop voltage control system. So here, the output voltage of a boost converter is sensed by means of some voltage sensor. The sensed signal is VOS, that is compared with some reference voltage. E is the error. The controller generates a control voltage VC or a control signal VC depending on the error. And the pulse width modulator produces a duty cycle pulse D, which will be usually proportional to VC. And that duty cycle is applied to the boost converter. Of course, the boost converter takes in the input voltage Vin. Let's say output voltage goes below the reference voltage, then VOS would have dropped. That would have increased the error E. That would have increased the VC. In a very simplistic way, the error goes up, VC goes up. So the duty cycle goes up in order to bring the voltage back to the original value. So this is a simple closed loop operation with the boost converter. Now if you take the boost converter, the DC gain of the boost converter is dV0 by dd, that is change in the output voltage for a change in the duty cycle. And if you consider D less than D max, This dV naught by dt is positive. That is, if duty cycle is increased, the output voltage will increase. If you consider operating point above duty cycle equal to Dmax in this region, then dV naught by dt is less than 0. So the polarity of the gain changes when d exceeds Dmax. Let us say that the operating point is to the left of Dmax. Then for a positive error, Vc will go up, duty cycle will go up, and the output voltage will be going up to restore the original value. By chance, let us say we end up operating on this side. That is when duty cycle is above Dmax. Here, if the output voltage is less than the reference voltage, then the error will increase, Vc will go up, duty cycle will go up, but the increase in the duty cycle will end up lowering the output voltage even more. Instead of negative feedback action, we end up with a positive feedback action. The error keeps increasing until the duty cycle goes close to 1 and gets locked up there. It is like placing the car in forward gear, but the car keeps going backward. Here, the closed loop system increases the duty cycle in order to increase the output voltage, but instead, the output voltage keeps going down. This can occur when you start the boost converter. When you start the boost converter, the capacitor voltage will charge to the Vin value. The reference voltage may be much higher than that. So there will be a large error in voltage between the reference voltage and the output voltage. So the error being high, Vc will be high. So duty cycle would have gone to the maximum value, maybe close to 1. You end up operating in this region to the right of Dmax. So the circuit may never start. So what is the solution? The solution is pretty obvious. Do not allow the duty cycle to go beyond Dmax. So place a limit on the duty cycle. That D limit should be less than Dmax. Another reason why you do that is as you go towards high D values, the losses in the circuit will increase, the efficiency of the boost converter will drop. So you should have some awareness of where the Dmax lies, and a limit should be placed on the duty cycle which is less than this Dmax. Dynamic response problem. This is the last problem that we are going to see. This is a very important aspect of how a boost converter works. As I mentioned earlier, this deserves a separate video or two. Since I do not wish to make this video into a very long video, I will just give the outline of the problem. This issue occurs in boost converter under CCM operation only. In DCM operation, this problem does not arise. It also arises in a few other converters, for example, buck boost converter. In a boost converter, we are varying the duty cycle and the output voltage varies correspondingly. Let's say this boost converter is placed in a closed loop voltage control system. You have various blocks in this control system, the boost converter and the load, the pulse width modulator driver, the filter to clean up the sensed voltage. Let us assume that this loop has reached steady state. That means the converter is operating under steady state, developing an output voltage based on the reference voltage. And the control problem is, given the boost converter and the load, the pulse width modulator driver, the filter, the voltage sensor, how does one design the controller so that the desired performance is obtained? That it should be stable. Error between the output voltage and the reference voltage should be minimum. The system should settle down fast for any changes or disturbances. That would be the dynamic performance. You have various blocks here. The most important block, of course, is the boost converter, and that's what we will focus on. Now let's see what we understand by the control to output transfer function of the boost converter. Consider a boost converter operating under CCM. It has an input voltage Vin and develops an output voltage V0 and feeds it to the load. The duty cycle is capital D. The DC output voltage is capital V0. The converter is operating under steady state. Now, let the duty cycle of the boost converter be perturbed a little. That is, it is operating under steady state. There is a particular duty cycle that is applied. It is developing an output voltage which is constant. Over this, a small perturbation is introduced in the duty cycle and the output voltage will vary correspondingly. So this is a perturbation or a change over steady state operation in a boost converter. That will tell us how the boost converter operates for small perturbation around the steady state. We can use that to define the small signal control to output transfer function. So the small signal control to output transfer function is given by V0 tilde S divided by D tilde S, keeping V in constant. We are not changing V in here. Here S is the Laplace variable or the complex frequency. Given small perturbation in duty cycle, how does the output voltage vary? We consider that ratio in the Laplace domain. V0 tilde of S divided by D tilde of S. That transfer function is given by this. This part is the DC gain. This is the numerator polynomial factorized here. This is the denominator polynomial. We can rewrite this in this form. The parameter Q, the parameter omega naught can be defined such that you get the denominator polynomial. Omega ESR is just 1 by RCC, and likewise omega RHPZ is 1 by this part. So V0 tilde of S by D tilde of S equals GDO times this numerator polynomial divided by the denominator polynomial. N of S is the numerator polynomial, D of S is the denominator polynomial. DC gain is GD0. That is V in by 1 minus D whole square. Notice that this DC gain is not V0 by V in ratio. It is obviously not. This DC gain is the change in the output voltage to a change in the duty cycle at steady state. It is the slope of the voltage curve V0 versus D. Now, this Q is the quality factor. It is defined as 1 minus D RL root of C by L. And omega naught is the resonant frequency, and that is 1 minus D by root of LC. So if you substitute Q and omega naught here, you will get this denominator polynomial. The values of S where the denominator polynomial goes to 0 are the poles of the system. So you just have to take the denominator polynomial, set it equal to 0, solve the quadratic in S, you will get the poles of the system. In this case, typically it will be a complex pair of poles. The values of S where the numerator polynomial goes to 0 are the zeros of the system. That we can easily see because the numerator polynomial is in factored form. So the 0 due to ESR will be minus omega ESR, which will be minus 1 by RCC. So if you substitute S equal to minus 1 by RCC, then this will become 1 minus 1, 0. So S equal to minus 1 by RCC is a 0 of this system. This term represents the 0 not due to ESR because of the boost converter structure and the switching. That 0 is the right half plane 0, and that will be equal to omega RHPZ, that will be 1 minus D whole squared RL by L. So if S equals 1 minus D whole square RL by L is substituted here, again the term will become 1 minus 1 and the numerator will go to 0. So these are the two zeros of the system. The dynamic response problem arises due to this right of plane 0 shown here. This is very particular to boost converter, buck boost converter, choke converter, and similar converters. Does not occur in buck converter or buck derived converters. Now we will see on the complex plane, on the S plane, where these poles and zeros are located. So S is sigma plus j omega. That is the complex frequency or the Laplace variable. This is the S plane. X-axis is the real axis, sigma, and the y-axis is the j omega axis. The denominator polynomial is a quadratic, and it will typically have a complex pair of roots, and we can plot them here, P1 and P2. Notice that these poles P1 and P2 lie on the left half of the S plane. The real part is negative. So the system is stable. If the real part had been positive, a pole on the right half of the plane, the system will be unstable. So boost converter, it's a stable system. It is possible to compensate for these to get good response when we design the controller. Next, we will take a look at the ESR0. That is S equal to minus 1 by RCC. That is on the left half plane. It's on the real axis on the left half plane. This does not pose a problem in the design. Last one, the right half plane 0, that is the culprit. It has got a positive value. So when you plot the right half plane 0 on the S plane, you will get it somewhere here. This is the ZRHP, which is a positive real value. This is difficult to compensate for. The main dynamic response problem is that it's difficult to design a controller with a boost converter to get fast response. We are going to see more about that now. I have shown the block diagram of closed loop output voltage control of a boost converter here. If you are controlling the output quantities, that is the output current or the output voltage, by varying the duty cycle, there will be a right half plane 0 present. That right half plane 0 limits the bandwidth of the closed loop system, limits the crossover frequency that you can achieve in this feedback system. Because of that, you cannot get fast response, period. If you are controlling the input current, then the right half plane 0 doesn't exist in the transfer function. The presence of the RHP0 in the transfer function makes it virtually impossible to design a controller such that the closed loop response of the boost converter for output voltage and output current under CCM is fast. So what can we do about it? We are engineers after all. I'm going to give a list of things we can do. But frankly, to be honest, there's nothing much we can do about it. It is an inherent problem in boost converter. One we can do is go for a higher switching frequency. Because when you talk of the speed of response, it is relative to the switching frequency. If you double the switching frequency, hopefully you can double the bandwidth you can get. There is a limitation. Obviously, you cannot keep increasing the switching frequency. The device will not permit it. The technology may not permit it. The switching losses may increase, and so on. Second is use smaller L, still operating within CCM. In other words, take the L closer to the CCM DCM boundary critical inductance value. If you reduce the L, you can see that the 0 goes further away from the imaginary axis. That will allow you to design the controller for a greater bandwidth. The problem is, of course, the ripple current, the delta IL in the inductor will increase. The losses in the converter may go up. Third is go one step further. Reduce the L so that the design is in DCM. DCM, it's perfect. There is no right half plane 0 problem. Of course, it is DCM. Currents will be peaky. The losses in the circuit will be higher. There will be an efficiency drop if you operate in DCM. A fourth option is to add an additional switch to the boost converter. This gives you an additional degree of freedom. And you can do the switching in such a way that the RHP0 is avoided. There is a converter called tri-state converter that tries to do it. Of course, there is some price to pay if you take this approach besides the additional switch. The fifth is to leave the boost converter totally and use a buck derived converter. Of course, you want to boost the voltage, whereas the buck converter steps it down. But you can use a buck derived converter with a transformer in it. One very popular candidate is forward converter, which is a buck derived converter, but it has a built-in transformer. You are using the switch for controlling the output voltage, but the main boost action is provided by the transformer. The last one is to be stoic about it, philosophical about it. Put up with it. Or use the boost converter in applications where the slow response won't be a problem. For example, in AC to DC converters used in laptop chargers, phone chargers, computer power supplies. So we need to have a last cartoon. So that has to be about right half plane 0. The right half plane 0 is the hero of this part. Why is the plane going so slow? It's all because of Mr. 0 on the right half of the plane. Remember, the right half plane 0 does not cause instability, does not make the boost converter, the closed loop operation, unstable. It makes it difficult to design a controller to get fast response. If you try to design a controller for fast response, you will land in unstable systems. With this, we have come to the end of this video. If you like this video and the series of videos, please click the like button and subscribe to this channel. Thank you.